This turns out to be quite an interesting series. So, when you first have a series, one thing to do is sort of get an estimate. So, what controls the top is 5 to the n. The most powerful thing in the denominator is 4 to the n. So we basically have this, 5 to the n over 4 to the n. Well, 5 over 4 is greater than 1, which means you're adding up things that are greater than 1. And then, that means it diverges. But 3 to the n, being an exponential function, is pretty powerful. So let's see. What is happening with this function? Clear. Thank you. So we've got 5 to the x divided by 4 to the x plus another 3 to the x. Another possibility we could use as an estimate is say, well, if I added these two together, that's approximately 7 to the x. So if we had, 7 to the n. So if we had 7 to the n for the denominator and 5 to the n for the numerator, 5 over 7, that's less than 1, so it would converge. Well, let's see. Can you just add them together like that? Technically, no, you can't. Change the window, 0 to 10. So yeah, look at the first 10 terms. And then 0 to 10. And the individual terms are just getting bigger and bigger and bigger. So this definitely diverges. The individual terms have to, in fact, be really, really close to 0 in order for this series to converge. This, if you look at this, you're adding up things like 2.4 plus 3.23 plus etc. etc. The series diverges. Now, how do we prove it? Well, I suggest that you have one of these at about this point in the semester, where you can look at the different tests, geometric, telescoping, is it a p-series, etc., and then see, for example, integral test. You want to integrate that thing? No, I sure don't. How about the root test? Well, taking the nth root of that would be a good idea. But what's the nth root of these two things added together? Well, if we have to do it, we could. Let's see, what else? What other choices? There's the ratio test, where you put in n plus 1 and you put in n. That's a possibility. You could compare it with something you already know diverges. You say, okay, this, we could say, I'm going to say that this one, 5 to the n over 4 to the n plus 3 to the n, is bigger than or equal to, because I'm trying to show that it diverges, I need to show that it's bigger than or equal to something that diverges. So something that diverges would be something like this. If it's a 5 over 4, that's bigger than 1, so that series would diverge. So we could try that. How about 5, 4 over, this is n, over 4 to the n. And then, actually the 5 to the n and the 4 to the n would cancel. We would have 1 over 4 to the n plus 3 to the n. Is that bigger than 1 over 4 to the n? And unfortunately, the answer is no, because this has more stuff in the denominator, so you're dividing by bigger numbers. The result is actually smaller. So scratch that idea. What else could we compare it with? Well, instead of trying to be all fancy like this and use 5 to the n and 4 to the n, maybe we just say, as we see from the graph, all of those are numbers that are bigger than 1. So we just say 5 to the n over 4 to the n plus 3 to the n is always going to be bigger than or equal to 1. Well, except for 0. Because if you have a 0 or a 1, if you have a 0, you're going to get 1 over 2, so that's not true. If you put a 1, it's going to be a 5 on top, and it's going to be a 7, 5 over 7. So for those first couple of values, 0, that's not bigger than 1. 1, that's not bigger than 1. But from that point on, so it's bigger than or equal to 1, for n bigger than or equal to 2. And as long as you can prove something's true from that point on, then the first two terms don't matter. It doesn't really matter if you're going to add in a 0.714 and a 0.5. If the rest of it adds up to infinity, the 0.5 and the 0.714 are not going to change that answer. So I just need to prove this equation. Let's see, so cross multiply, so 5 to the n is bigger than or equal to 4 to the n plus 3 to the n. Now the thing is, I know this equation, this inequality is true. I could see that from the graph and looking at those numbers. But how do you prove that 5 to the n is always bigger than a 4 to the n plus a 3 to the n? Well, what could you do? You could say, well, I know that it's true at some point. You could then take the derivatives and say, how fast is this one growing compared to how fast is that one growing? If this one is bigger than this one at some point, and you can prove that this one is growing faster, or it has a bigger derivative, then the inequality has to be true. The only problem with that is, what's the derivative of 5 to the n? Well, it's 5 to the n times the natural log of 5. That means you would then have to prove that 5 to the n with natural log of 5 is bigger than these guys with natural log of 4 and natural log of 3. So the derivative is essentially the same as the original. So taking derivative is not going to help. All right, then what we do is, this is called a proof by induction. What you do is you say, okay, I know that it's true for 2. So it's sort of like climbing a ladder. You say, all right, here's n equals 2. I can plug in a 2, and I would get 5 squared. Is that bigger than or equal to 4 squared plus 3 squared? So is 25 bigger than or equal to a 16 plus a 9? Yes, because they're equal. So yes, it passes that. Then what you do is you say, okay, prove that if it's true at some level n, so assume that it's true at level n, and then I can prove that it's going to be true at level n plus 1. Then essentially what that does is say, okay, I know it's true at 2, and that this part right here, the induction part, means that from whatever level you're at, the next level is also going to be true. So then you know n equals 3 is true. And then because of this idea, that means the next level, n equals 4 is true. And then the next level, so that means you could go forever and ever all the way up the ladder. So the next part is assume that it's true at level n, I now have to prove that it's true when the n's become n plus 1s. So in order to get this to be 5 to the n plus 1, just multiply both sides by 5. So you'll get 5 times 5 to the n. Because 5 is positive, I don't need to change the direction of the inequality. And then multiply the right side, so 5 times 4 to the n plus 5 times 3 to the n. And then this side is 5 to the n plus 1 Now this side over here is supposed to say 4 to the n plus 1 and 3 to the n plus 1. So in other words, for this case right here, or this level, everything has to have n plus 1. N plus 1 and n plus 1. Well, notice this. If you're multiplying by a 5 right here, that result will be bigger than if you had multiplied by a 4. Since 5 is bigger than 4, when you multiply by 5, the result is bigger than when you multiply by 4. And you can do the same thing here. If I replace this with a 3, I'm going to get something that's smaller. Or in other words, when you multiply by a 5, it's bigger than when you multiply by a 3. So if you look at this inequality we have right here, 5 to the n plus 1 is bigger than or equal to 4 to the n plus 1 plus 3 to the n plus 1. All right, so it passed the second step, or the induction step of the proof. That means that this inequality is always true. That means that when you add up all of these terms, they're going to add up to more than or equal to 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 forever. Therefore, it diverges. It's a bit of a tricky one, but that was fun.